Welcome to yet another video on our channel Euclid Mathematics. We have started lecture series on CSIR NET SET and Gate previous year question paper along with their topics. So here in my today's video, we are going to learn one of the concept which is from ring theory. So already I uploaded plenty of the videos on irreducible polynomial, which is very much important topic in a ring theory that we need to understand first of all the definition of an irreducible polynomial, and then we'll move for some examples which is the based on irreducible polynomial. So let's get start our today's solution. I will explain to you all definition along with the example. We have the question which is from the ring theory, which is completely based on irreducible over some ring. Okay. So here we have polynomial f of x is equal to x square minus 2. And then we have to check whether it is irreducible over q or not. Okay, and after that we also have to check whether it is irreducible over r or not, because this topic is very much important. Every year there is a question on the SET exam, NET exam. Okay, so definitely question it comes on this topic. So already I uploaded definition and other examples depend on irreducibility and reducibility criteria. So if you wanted to check this video, you may check it into my playlist. So the definition of irreducibility, it says that in simple language I will explain to you all. So here if we have polynomial f of x is equal to x square minus 2, okay, and we have to check whether it is irreducible or not. So for that we have to check it is a non-zero non-unit polynomial from our ring. Okay, so fx, we can factorize fx, which is equal to some other two polynomial. Fx can be factorized into gx into hx. Okay, so we can factorize polynomial fx as a gx into hx, but one condition it is there that either gx or hx need to be a unit element. Okay, the definition of unit element already I explained in my lecture, previous lecture. Okay, so you may check these videos on my channel. So along with the example I explained there. So the fx into gx can be factor, it is the factor for fx. Okay, fx can be factored into gx into hx, but gx or hx, one of them need to be a unit element. Okay, and one more definition we can say that fx can be factorized into gx into hx, but gx and hx both not be there in our ring. Okay, so if this condition hold, then we say that our given polynomial is irreducible over our ring. Okay, so and one, our fx need to be a non-zero and non-unit polynomial. Okay, this condition need to be hold here. Fx non-zero non-unit polynomial need to be there. So now let's show that fx is equal to x square minus 2, it is whether it is irreducible over q or not. Okay, or it is irreducible over r or not. So here our definition of fx, it's irreducible polynomial. It says that we have to factorize f of x if it is possible. Okay, so if f of x it is possible to factorize, then go for factorization. If it is not factorized, then surely we know that we can factorize by 1 multiplied by fx. Okay, so if one of them is unit, that means one number 1, it is a unit element. Okay, so that means we can say that it is irreducible. But now here we can see x square minus 2, we can factorize it. Okay, so I written here x square minus 2 as a x square minus square root of 2 bracket square. Okay, so we have to find out the factorization of our polynomial only. Okay, so here we can see that x square minus square root of 2 bracket square, like a square minus b square, that can be expanded as a minus b into a plus b. Okay, so x minus root 2 into x plus root 2. So this is the factorization of f of x, which is a gx into hx. So it seems like that gx, which is x minus root 2, and hx, x plus root 2, both are the polynomial. Both are polynomial. So we cannot factorize this f of x other than some multiplication of a unit element. Okay, so x minus root 2, x plus root 2, both are the polynomial. So consider this is gx is x minus root 2 and hx is a x plus root 2. Okay, I got the gx and hx, but we have to check that root 2 which lies in a q of x. Okay, a rational polynomial. Okay, so is it possible that x minus root 2, x plus root 2 which belongs to q of x? No, it is never possible, because q of x does not belong such type of the numbers. Okay, so it goes to its complement, q of x complement. So x minus root 2 and x plus root 2, it is not there in a q of x. So we can factorize f of x as a g of x into h of x, but g of x and h of x both are not there in our ring. Okay, our ring it is here over q. Okay, So if their factorization it is not in our ring, then surely we say that our polynomial f of x, which is equal to x square minus 2, it is irreducible over q. Or in simple language, if we can factorize our polynomial and we got the root from our polynomial and this root which not belongs to our ring, then we say that it is irreducible polynomial. Okay, so it is the easier definition. There are some certain other criteria there, that some tests are there. For example, like Einstein's irreducibility criteria, again mod p test. There are multiple other tests that is much useful, very much useful here to verify our polynomial is irreducible or not. Okay, now let's check out whether this polynomial which is irreducible over q or over r or not. Okay, and surely we can see that we have only one condition: this belongs to rx, this belongs to rx. Okay, root 2 always goes to the rx. Okay, so that's fine. For this 2 polynomial, it is not irreducible over q because we got the factor of our polynomial and this factor belongs to our ring. Okay, so let's see the detailed solution. So here we have polynomial f of x is x square minus 2. It's a factor gx into hx, x minus root 2, x plus root 2. Okay, so I got the two factor of from fx, and the g of x is here x minus root 2, hx is here x plus root 2. Okay, so we can say it here that x minus root 2 which belongs to r of x and x plus root 2 also it belongs to r of x. That means the definition of irreducibility criteria is violate here. Our definition of irreducibility criteria, it says that the factor from fx which is a gx into hx which not to be there in rx. If it is not there in Rx, then we say that our polynomial it is irreducible. But here we got the inverse condition. They are polynomial factors of our polynomial which belongs to our Rx. Okay, so then we say that our given polynomial f of x is x square minus 2 is irreducible over q. Okay, because neither g of x is a unit and h of x is a unit. Okay, g of x is not unit or h of x is not unit, or the polynomial which belongs to Rx. So these are the two definition I applied here in order to check our polynomial is irreducible or not. Now let's check one more example. Okay, so that example it is like a third fourth power, because when power increases in our irreducibility criteria, that verification of irreducibility it goes much more difficult. So it is I'm going for third cube. Okay, now right now, so we will check for power 3. So in our power 3 we have third example. Next example, our polynomial is x cube plus x square plus x plus 1, and we have to check whether which is belongs to polynomial integer zx is irreducible over z or q it is there or not. Okay, so we have to check this polynomial is irreducible over z or q or not. Okay, so f of x is here x square plus x cube plus x square plus x plus 1. Try to factorize our polynomial and take this polynomial fx as a gx into hx and verify our given definition it is applicable or not. In some condition definition also not applicable, so these types of the example we use some standard criteria for irreducibility of polynomial. Okay, so these are the standard tests that we are going to learn after this point, these standard tests, how we can apply this standard test to our example. Now first of all understand some example which based on definition. Now here f of x it is written here, and there are factors. I taken x square common from this first two, so x plus 1 left over here plus x plus 1 it is here. So f of x is a x square plus 1 into x plus 1. Now we can see that f of x can be written as g of x into h of x. Okay, so x square plus 1 it is also integer polynomial because it do not have like a root 3, root 4 or 1 by 2 type of the fractional part. And we know that integer polynomial always belongs all numbers like 1, 2, 3, negative 1, negative 2, negative 3, 0, like such an element, and which also belongs to q of x. So g of x is having root and which all goes to the integer polynomial. Okay, so f of x, the first integer polynomial, it goes to zx or q of x, and h of x it also goes to zx over qx. Okay, zx or qx. So if g of x and h of x both belongs to our given ring, then we say that the definition of irreducibility criteria is violated here. So neither g of x is a unit or neither h of x is unit in zx or qx. So if both of these are not unit, and one more condition that their factors which belongs to our ring. So both part of the definition which violate here, then we say that f of x, which is x cube plus x square plus x plus 1, which is not irreducible, that means which is a reducible over zx or qx. So see that how easy these examples are. We just have to factorize our polynomial, and we have to check whether these roots which belongs to our ring or not. If it is belongs to our ring, then it goes to reducible criteria. If it is not there in a ring, then it is a irreducible. Okay, it is a irreducible polynomial. This is only the definition we have to apply here. Now I have one more example that you all have to try for your homework. Which one is here as a f of x as a x cube minus x square plus x minus 1. Okay, and check whether this polynomial is irreducible over zx or qx. Okay, so zx or qx, we have to check whether it is irreducible there or not. Okay, so after that their solution just have to factorize. I written here solution. If you wanted to check, you may check this one. Okay, so this is the factorization of g of f of x gx into hx, and g of n h of x which belongs to z of x. So neither g of x is unit nor g of h of x is unit, or there are two factors which belongs to z of x. So we say that f of x is a reducible over z of x or over q of x. Okay, so because their factor belongs to our ring, or none of them is a unit, that's why it is irreducible over z of x or q of x. Now let us see one more example. So here it is irreducible over z of x or z over q. Okay, so I have one more example, x cube plus 1. So a cube plus b cube, you have to apply result for a cube plus b cube, which is a plus b, a square minus ab plus b square, and a cube minus b cube, a minus b, a square plus ab plus b square. Apply these results here and just figure it out whether x square plus 1 is irreducible over our zx over qx. Okay, so we have given our question, we have to check whether it is irreducible over zx over qx or not. And similarly, I taken one more example, which is a x cube minus 1. Okay, x cube minus 1, and we have to check whether it is irreducible over zx or qx. Okay, so we just have to factorize our polynomial g of x into h of x, and we have to show that both of these are not belongs to our ring, or none of them is a unit. So in this condition, we say that it is the reducible polynomial. Okay, it is the reducible polynomial. Now here we can see that their factorization, it belongs to our ring, and none of them is a unit. So we say that here neither g of x or h of x is a unit in a zx. So f of x is here x cube minus 1. It is a not irreducible polynomial over z of x or q of x. Okay, so that's it for our today's definition of a irreducible polynomial. That we have to apply the definition of two conditions from our definition to our example, whether our polynomial is irreducible or reducible. But I have some of the example that can be quite easier. Difficult because we cannot apply easily definition. If you are going to apply definition over there, it is quite a bit time taking and challenging for us. We can solve these examples surely by definition, but if we apply some test like a irreducible criteria, such a test if we apply to our example, we'll get that irreducible or reducible condition in easy way. Okay, so that's why these tests are very much important. So in my next lecture, I'm gonna explain to you all some tests from the irreducible criteria or reducible criteria. Okay, so that's it for our today's lecture. I hope you all have understood my today's lecture. This is everything for you all. Okay, so thank you everyone. Thank you for my today's lecture.